This is an electronic expansion valve from a refrigeration system, but this type is electronically controlled using a stepper motor. So we're going to look inside one to see how it works. When we look at a typical refrigeration system, we have the compressor, the condenser, the expansion valve, and the evaporator. The condenser and the evaporator are both heat exchangers. The condenser sits outside the property, and the evaporator sits inside the room being cooled. The compressor circulates a refrigerant in the pipework, which cycles between all of these components. The expansion valve regulates the flow of refrigerant. The refrigerant is a specially designed fluid which can change between being a liquid and a gas very easily. And that's because it has a very low boiling point. For example, refrigerant R410A will boil at negative 48 degrees Celsius or negative 55 degrees Fahrenheit, although this will change with pressure. But if the refrigerant is inside a pipe within a room, and the room is at 30 degrees Celsius or 86 degrees Fahrenheit, then this will be more than enough to cause it to boil from a liquid into a vapor. By the way, if you want some refrigerant charts, you can download these for free from our website. I'll link to these in the video description down below. So the refrigerant is entering the evaporator as a low pressure, low temperature liquid vapor mixture. It flows on the inside of the pipe, and at the same time, a fan is moving the ambient air of the room over the outside of the pipe. This causes the refrigerant to boil. It will absorb the heat from the air through the pipe wall, and then it evaporates. As the refrigerant evaporates, it carries away the heat. It's similar to when we boil water. The water heats up, it evaporates and turns into steam, and carries this heat away. So the air on the outside is entering hot and it's leaving cold. The refrigerant continues to travel through the evaporator, picking up more heat, which boils it further until it becomes slightly superheated. This basically means it's now completely gas and doesn't contain any droplets of liquid refrigerant. Liquid damages the compressor, so we want to ensure it can't reach the compressor. The compressor sucks in the refrigerant, which is leaving the evaporator as a low pressure, low temperature, slightly superheated vapor. It then squeezes this together into a much smaller space, and so the pressure increases. All the heat which was picked up in the evaporator is now contained in a much smaller volume, so the temperature will increase. This is very important, and we will see why in just a moment. But if you've ever pumped up a bicycle tire, you will notice the pump becomes hotter as it's compressing the air. The refrigerant is then pushed into the condenser, where it enters as a high pressure, high temperature, superheated vapor. The condenser is located outside, and the outside air might be very warm on a summer's day. As heat always flows from hot to cold, we need to ensure that the refrigerant is hotter than the outside air. Otherwise, the unwanted heat will not be able to leave the refrigerant and leave our system. A fan will help to blow ambient air over the condenser to remove this heat. So the outside air is entering warm, picking up heat and leaving hot. As the heat is removed by the air, this causes the refrigerant to condense back into a liquid. It's a little bit like when steam hits the window on a cold day. The window is cold, so it condenses the steam from a vapor into a liquid, and then this liquid starts to run down the window. The refrigerant therefore exits as a high pressure, medium temperature, saturated liquid, and this heads to the expansion valve. The expansion valve needs to regulate the amount of refrigerant entering the evaporator to control this superheat. If it allows too much refrigerant to flow, it can flood the evaporator, so the refrigerant doesn't evaporate and liquid reaches the compressor and possibly destroys it. But if it lets in too little refrigerant, the system won't provide enough cooling, and so it operates inefficiently. The expansion valve regulates the refrigerant by only allowing it to pass through a small hole. This creates a large pressure difference across the valve. One side is the high pressure liquid, the other side is almost empty. The small hole causes it to almost spray into the evaporator as a part liquid, part vapor mixture. The refrigerant will expand to try and fill the empty space on the other side, and this will cause it to drop in pressure as well as temperature. It's a little bit like spraying a deodorant can or a spray paint can. It flows through a small hole, causing it to expand as a part vapor and part liquid mixture, and then we can feel the can become cooler. Now, the original method to control this was by using a fixed orifice device, and you might still find these on the back of your refrigerators. The hole within this device was a fixed size, so the entire system would simply turn on and off to meet the cooling demand. It does work, but we can't maintain a stable temperature control because the system is simply turning on and off. The next evolution was the thermostatic expansion valve. This is still widely used today, and it senses the superheat at the outlet through a bulb which is filled with another refrigerant. This other refrigerant will expand to close the valve when the superheat is too high, and it condenses to open the valve when the superheat is too low. This type of valve needs to be manually calculated and adjusted by a technician. It does work very well, but it's prone to mistakes. It also takes a long time to calculate and set up, and it is also only adjusted once per service visit, which is not ideal. It will also not allow peak performance. However, it does work very well, and these will continue to be used for many years. And so the latest evolution is to use electronic expansion valves. These use a controller to measure the exact temperature and pressure and adjust the valve position automatically in real time to ensure optimal performance and maximum system efficiency. This model is based on the ETS5M, which is produced by Danfoss, who have kindly sponsored this video. They have also made a detailed video discussing the different types and uses of electronic expansion valves, which is hosted by their expert Victor. There's some very good information discussed here, so do check it out. I'll leave a link in the video description down below for you. Let's look at a simplified version of the valve to see how it works. First, we have the valve body and the stator housing. These two can be separated, which allows the stator to be replaced if needed, and because the valve body is sealed, no refrigerant leaks from the system, so repairs are quick and easy. Inside the stator, we find a number of coils of copper wires, which are wrapped around the inner perimeter. These are the stator coils. Then inside the valve body, we first have the permanent magnet, which is connected to the shaft. The shaft runs the length of the valve. Partway down the shaft, we find a threaded section. At the bottom of the shaft, we find the valve needle, which pushes against the valve outlet to close it. The permanent magnet and shaft will sit concentrically within the stator. These are separated by the valve body. The permanent magnet rotates, which causes the shaft to also rotate. The threaded section of the shaft sits within the threaded section of the shaft holder. So, as it rotates, it causes the shaft to move up and down, which opens and closes the valve. The valve opens and closes to regulate the flow of refrigerant. The controller sends pulses to the stator, which is essentially just a stepper motor. These pulses energize the different coils, which create small magnetic fields. We know that magnets interact. The alike ends will repel, while the opposite ends are attracted to each other. When we pass electrical current through a wire, it creates an electromagnetic field. If we wrap the wire into a coil, it creates a larger, stronger magnetic field. So we can vary the polarity of the field by reversing the direction of current. We can turn the electromagnetic field of the coil off simply by switching the power off. But a permanent magnet is always on. Now, if we place a magnet at the center, we can use other magnets to rotate this. We can also place coils around the magnet and control its direction by controlling the magnetic field created by the coils. The more coils we use, the more precisely we can control the magnet's rotation. We also know that if we align a bolt with a threaded hole and rotate the bolt, it will drive into the material. We can reverse the rotational direction and remove the bolt. So if we connected a magnet to the top of the bolt head and use the coils to create a rotating magnetic field, we can convert rotation into linear movement. At the top of the shaft is the permanent magnet, which is surrounded by the coils from the stepper motor. As the coils energize, it causes the permanent magnet to rotate, and this rotates the shaft. The shaft has a threaded section, which causes the shaft to move up and down. This closes the valve and controls the flow of refrigerant. At the outlet of the evaporator, we find a temperature sensor and a pressure transducer. These are constantly measuring the refrigerant. The controller is reading this signal and converting the pressure to find the saturation temperature of the refrigerant. This is using refrigerant data which is stored in the controller. The pressure reading is converted into its equivalent temperature for that refrigerant. This is then compared to the actual temperature being measured. The difference between these two is the operating superheat. The controller then decides if the valve should open further to allow more refrigerant or close slightly to reduce the amount entering. The controller then sends this signal to the expansion valve stepper motor to energize the coils and create the electromagnetic field. The permanent magnet's magnetic field will interact with this, which causes it to rotate either clockwise or counterclockwise depending on the signal being sent. The signal causes the valve to rotate a very small amount, which allows precise control and adjustment to the superheat. When the cooling load on the evaporator suddenly increases, the refrigerant is going to boil much faster. There isn't enough refrigerant currently inside to cover this demand, so the suction line temperature and pressure will increase. The sensors detect this, and so the controller tells the valve to open further to allow more refrigerant into the evaporator. When the cooling load decreases, the refrigerant will boil more slowly, so there will be too much refrigerant inside the evaporator. The temperature and the pressure will therefore decrease. This is detected and the controller tells the valve to close further to reduce the amount of refrigerant entering the evaporator and maintain the correct superheat. So it can provide very precise automated control of the superheat. This particular valve has purposely been designed to be small, which makes it perfect for installations within crack units or computer room air conditioners, as well as heat pumps and variable refrigerant flow systems. Don't forget you can find out more by visiting the Danfoss video. The link for this is in the video description down below. Okay, that's it for this video, but to continue learning about HVAC and refrigeration engineering, click on one of the videos on screen now and I'll catch you there for the next lesson. Don't forget to follow us on Facebook, Twitter, LinkedIn, Instagram, as well as theengineeringmindset.com.